This presentation is an overview of prior art LUT-based FPGA tools compared to CXI ECA tools. This is the second of 4 presentations describing Element CXI hardware and software. The architecture presentation focused on fundamental comparisons with prior art and CXI innovations from a hardware perspective. This presentation covers software tool expectations as established by the reconfigurable device market in the last 25 years. The advanced features presentation will describe new features found in the ECA, which have no comparable basis in prior art. And the IDE presentation will illustrate what's necessary to meet and exceed expectations to succeed in the mature reconfigurable device market. Your presenter is Stefan Wasson, a founding member of Element CXI's engineering team with 35 years digital logic work experience in Silicon Valley, 25 years focused on reconfigurable logic, architecture, and tools design, and more than 20,000 hours using reconfigurable design tools, including tool evaluations and designs for such clients as Concurrent, Cadence, Vantas, and Xilinx, where I taught over 100 classes. I've also published over a dozen papers on programmable logic design, implementation, and tool use. The CXI material in this presentation is covered by the following patents. The purpose of this presentation is to describe reconfigurable logic design tool flow conventions and expectations, discuss the strengths and weaknesses of prior art tools, and establish the applicability of these tools to the Element ECA architecture. We are well advised to understand the strengths and improve upon weaknesses of existing tools. Only with such background can competitive tools be created. As we shall see, the primary differences between the CXI and LUT-based prior art FPGA tools are cycle-accurate operation, implementation, constraints, and analyses. Pretty much everything, you say. Well, yes and no. This presentation is organized into the following topics: roadmap options. The route taken predetermines the kind and quality of tools needed. Standard operating procedure, an example of the usual route. Design flow, the existing tool flow for reconfigurable logic arrays of the LUT-based kind. Summary, a list of relevant distinctions from FPGAs in CXI tool flow requirements. And conclusions, understanding what to leverage and improve, what to avoid, what to add, and where to raise the bar. The type of tools needed depends on the company roadmap of options. We can build IP or an IC. Building IP, we can deliver functions, algorithms, or fabric, architectures. We can build silicon as either a captive house, consultants, or as an OEM, chip provider. As fabric providers, we can deliver either soft IP, fabric generators, or hard IP, fixed fabric. As a chip provider, we can stay small and sell to a few customers, or grow large and sell to many customers. Different goals require different tools. Assuming we do not pursue soft IP, a very tough sell without prior working silicon, in general, the amount, sophistication, and quality of tools needed is directly proportional to the number of simultaneous users served. For algorithm design, only third-party tools are needed, not CXI tools. Fixed fabric and contract designs are, by definition, custom. Hence, tools tailored with and subservient to customer collaboration are needed. To support a small number of users, we can rely on in-house expertise and a modest tool set, but to support more users than in-house staff can handle, and to compete in the real worldwide market, a first-class tool suite is needed. Now, these are not mutually exclusive options. Indeed, the former fund and pave paths to the latter, with increasingly sophisticated tools leading to increasing design wins and increasing company success. This presentation assumes the superset goal is to serve many customers. Here's one view of the standard operating procedure for building a product. Most of you have probably seen some variation of this iconic example for a tree swing. What marketing is thought to have requested, what engineering specified, what got built, what got installed, and what the user actually wanted. Of course, the moral is, a lot can be lost in translation without a good process. Good standard FPGA design process is little changed since I taught this 12-step program at Xilinx and published it in Integrated System Design as follows. Perform market research, document the requirements, specify the functionality in engineering terms, partition specified functionality into one or more devices, implement the partitions with schematics, HDLs, etc., simulate the behavioral implementation, apply physical and temporal constraints, compile the design into targeted devices, simulate gate-level results to ensure conservation of functionality, analyze timing to make sure performance targets are met, download the bit stream into a device on a test bench board in the lab, bring it up, the polite euphemism for debug, because things rarely go right the first time, and finally, archive any and everything needed to recreate the project. Of course, ideally, this is a straight shot from top to bottom, with little iteration at each step. But realistically, there are iterations between adjacent steps, and in the worst case, many iterations up and down the entire process. This mature use model has been established over 25 years, billions of dollars, and tens of thousands of users. All of these steps are applicable in some form to ECA design implementation, as we will shortly discuss. But first, a little levity. In the product research phase, marketing tries to pin down what the customer wants. After exhausting queries from a representative sampling of customers, the requirements are documented. These requirements are then magically converted into an engineering specification in a time-honored tradition called rolling the spec downhill, usually from hardware to software to the app's user. Of course, the process works better with some feedback between the groups, in both directions. In the beginning, it's a bit of a chicken and egg problem, except as CXI's Brian Box notes, usually there's 3 chickens and no egg. Without collaboration, hardware may spec something that can't be programmed, software may spec something that apps can't use, and apps may spec something that can't be built. But with collaboration, everyone's nuggets of wisdom eventually evolve into a working spec. After the spec, the first task is partitioning the application. In the old days, the simplistic approach often went something like this. Jane, you do the video compression engine. Bob, you do the DMA controller. Verbally and manually partitioning disparate functionality into separate devices. For example, given 4 functions of different size, interconnected horizontally, vertically, and diagonally, it's easiest to partition the lot by allocating them each to their own device. And this was how it was done when devices were small. But with increasing part size and resource availability, integration into a single device becomes practical, with this internal partitioning manually defined by user-supplied constraints. It's worth mentioning that one of the vulnerabilities of partition integration is the degradation of individual function performance because of the inevitable competition for overlapping resources. In today's FPGAs, independently verified IP may not run at speed when integrated with other IP. Performance degradation is also suffered integrating functions interconnected in directions that go against the device's natural data bus orientation. Besides an amenable architecture, what's needed is a top-level partitioning tool to manage IP integration while maintaining IP performance. After partitions are decided, The application functions need to be implemented accordingly. I want to clarify that this presentation is not focused on chip design, but in particular app design for implementation in a chip, and in general, of course, revenue for the company. Traditionally, FPGA implementation methods comprise two forms: graphics, including schematics, flowcharts, bubble diagrams, Karnaugh maps, and tables, and text, including hardware description languages like Verilog and VHDL, and less successfully for LUT architectures, programming languages like C and its deviants. Text-based tools do have an advantage in being architecture agnostic, but this generality is also their weakness. For example, analyzing this small CIR filter coded in pure C, automatic loop unrolling into fully parallel paths generates 11 registers, 24 multipliers, and 33 adders. But the same loop can be unrolled into a pipeline of just 7 registers, 4 multipliers, and 4 adders. The analysis for this example may be found in my paper C transcode example.doc. The C derivative code generators that have not outright perished have not compared well to traditional HDL entry. For example, for one of CXI's simpler elements, the triple ALU, a comparison of the amount of code, gates, and logic levels generated by Handle C-based BlueSpec and by Coware's SPW against handwritten Verilog shows the code generators create 1 to 2 orders of magnitude more code, 3 times as many gates, and 10 to 30% more logic levels. Besides its inefficiency, such generated code is obtuse and difficult to understand, worse to simulate, and nearly impossible to fix. Graphic-based tools have the advantage of topological similarity, which enables significant area and performance efficiencies. CXI's ECA is particularly amenable to graphics-based implementations because of the architecture's medium granularity and hierarchical regions. Schematics and block diagrams are superior for data flow implementation, but they are less efficient at defining control logic. Schematics do offer partitioning constructs not readily available in HDLs. Here's a Xilinx configurable logic block primitive. Referencing its I/O ports permits direct manipulation of LUT contents in a pop-up dialog box by filling in fields defining the LUT mode, output source, and equation. This construct, circa 1991, is essentially obsolete. No engineer in their right mind would now attempt to implement a large fine-grained design with such a partitioning construct. Flowcharts are a better way, not just to represent, but to implement simple control logic. In 1989, at Highgate, I created a compilable flowchart symbol set, first in FutureNet, then in ViewLogic. For example, this flowchart is functionally identical to the previous FSM schematic. Ironically, 3 years after I presented this compilable symbol set to Xilinx, they contracted me to verify their version, which they called XBlocks. Still, this is not the most efficient way to implement complex control logic. Compilable bubble diagrams are a little better control flow representation. They make clear the next state optimization opportunities, but they do have some difficulty optimizing resource sharing. They're also subject to the usual FSM vulnerabilities, next state conflicts, omissions, and erroneous defaults. Consider this diagram for a PCI target predicated upon the Rev 2.0 PCI local bus spec. In particular, look at the 4 transition equations out of busy, as given in the spec. The problem isn't immediately apparent here, but it is readily exposed with Karnaugh maps. Extracting the 3 primary variables into an 8-cell map, equation 1 specifies to remain in busy if not frame pound or not iReady pound and hit is false. But equation 2 specifies to go to idle if frame pound, a clear conflict. Furthermore, equations 3 and 4 specify where to go when hit is true, and not frame pound or not iReady pound. Another clear conflict. Integrated Systems Design published my detailed analysis of this PCI spec error, along with additional map manipulation features of value to the FPGA graphic toolkit. Another valuable graphic implementation tool is the compilable table, like this one, which I created in 1995 in ViewLogic for the PCI contract for Xilinx. Once filled in, the table performs a corner turn to slice out bits for ROM preload of each register. Simply selecting a hex character in the table and executing a change component command on the command line, the user can easily preload all the base address registers. In fact, Xilinx liked it so well, they patented it. I also recommended that they automate the process, and the LogicCore program was born. Nowadays, such macro generators are the preferred implementation method. For example, here's Altera's floating point square root macro generator. Select precision and latency, push the button, and voila! Generated code ready for compilation. And assemble if you prefer block diagram entry. There's also a helpful resource utilization estimate to help you decide beforehand if you actually want to use the generated module. Altera's Wizard Manager offers a plethora of functions, from general arithmetic to memory, and more complex functions like processors and peripherals. For example, under memory compilers are a multiplicity of options. Let's take a quick look at FIFOs. You can select options like bit width, word depth, and read-write synchronization, full, empty, and other flags, which physical memory resource you'd like to use, speed versus area optimization, and overflow-underflow protection. Let's take a look at something a little more complex in Altera's DSP folder, the FIR compiler. Here you can parameterize things like the rate, number of channels, input number system, input bit width, output method, output number system, coefficient scaling, and bit width, device family, arithmetic structure, pipeline levels, and which logic resources you want to use for data storage and coefficient storage. In return, you get code and a resource utilization estimate. Now let's look at one of the so-called megacores, an embeddable soft processor, the NEOS. You can customize your processor by selecting the economy, standard, or fast model, which have progressively more features, performance, logic, and memory. You can select the multiply resource and the memory resource for reset and interrupt vectors, specify instruction and data cache sizes, choose advanced features regarding interrupt controllers and exception handling, define MMU and MPU settings, select from not to lots of JTAG debug support, and you can add custom instructions. Just FYI, Altera's NEOS soft processor is the invention of my Highgate design associate, Brian Hoyer. Hoyer is also the inventor of Altera's System on a Programmable Chip, or SOPC, an IP integration tool, a very high-level abstraction tool for integrating many wizard-generated components. For example, the NEOS CPU we just reviewed is shown here connected with predefined standard memory mapped interfaces to a handful of components like data RAM, PIO, and a JTAG UART. You can expand the view to show all and manipulate any intermodule connections. Connections are shown using a solder dot diagram. Clicking a full dot breaks a connection. Clicking an empty dot makes a connection. You can remove modules from service, generate and add new ones, and edit existing ones. Then, after all IP is integrated, the SOPC environment allows the user to generate an address map. A table of masters and slaves indicates all the base addresses and ranges for each relationship, and any address can be edited here. Okay, that's enough macro generators for now. Summarizing implementations. Advanced design environments offer a multiplicity of methods. A hybrid hierarchy of appropriate abstraction levels. Macro generators. Hardware code. Software or assembly code. And diagrams. And no matter the view, recognizable names must pass into the netlists and thence to waveforms for ease of simulation and analysis. A significant failing of auto-generated code. Just take a look at the first 60 lines from this 10,000-line auto-generated equation. How are you going to simulate that? The next of the 12 steps, simulation, can be performed on a logical or physical netlist. In orthodox FPGA design flow, simulation is traditionally performed twice, before compilation on the logical netlist and after compilation on the physical netlist. A major difference between the two is pre-compilation simulation does not include the effects of placement, which in a standard FPGA includes things like route delays and signal loading. Since full timing is unknown, this step proves functionality, not performance. However, if the netlist is structural and the connection delay is known a priori, performance can be pre-calculated. The CXI architecture offers this opportunity. In the most rudimentary simulation environments, the unit under test netlist is stimulated with desired vectors and resulting outputs are inspected. The traditional inspection method is through waveforms, one for every netlist node, every gate, often tens of thousands of them, most of negligible relevance. More contemporary test benches compare unit under test output to an identically stimulated gold model. Two of the major assumptions in this environment are the stimulus is adequately representative of the real world, and the gold model is gold, that is, completely representative of desired functionality. Of course, this test bench just demonstrates that what has been checked works, not that what works is all that should be checked. Checking behavior is frequently performed using visual inspection tools from third-party vendors like MathWorks. Here, a simple counter is shown, incrementing from 0 to 4 repeatedly. But as previously forewarned, here functionality is shown, not performance. Note the unlabeled horizontal axis. It could be clocks, cycles, samples, any time event, but it is typically unrelated to the physical reality of real-world constraints. Constraints in the real FPGA world have gotten, shall we say, complicated, as this list of Altera constraint options attests. There are options for anything and everything, and things you didn't know you needed options for. There are options for every aspect of compilation, synthesis, analysis, and report generation. Options for effort level settings, resource utilization, netlist optimization, state machine protection, memory equivalence, DSP balancing, register retiming, logic duplication, metastability optimizations, and the ever-popular magic initial placement seed. And this is just one list of constraint options. However, we'll limit this presentation to the basic constraint methods and applications. Constraints can be applied through GUI menus, HDL pragmas, schematic attributes, or simple text files. Generally speaking, these are applied to control partitioning, placement, and timing. Partitioning constraints apply hierarchically to combinatorial logic, components, and modules for the purpose of controlling placement. Placement constraints are either absolute or relative, and most often apply to logic for the purpose of influencing timing. And timing constraints apply to clock nets, typically, to specify their frequency or domain, to general nets to specify criticality, and to I/O signals to specify margins. The most onerous of these are inapplicable and unnecessary to the CXI architecture. But let's look at them anyway to see what the typical FPGA user assumes is required. Schematics have offered the very lowest level control. For example, combinatorial logic can be mapped, partitioned, together into a common LUT. That block's location can be fixed in the logic array exactly, or by exception, in a specific column or row, or within a rectangle or a group. Signals can be locked to specific LUT pins, components can be named, and nets can have attributes attached to them. For example, the asynchronous reset net can be marked as non-critical. Signals can be marked as external, which means they remain visible for simulation observation, and a high fan-out net like parallel load enable can be forcibly assigned to a long line resource. The CXI ECA doesn't need net weighting or pin locking, but it does benefit from a location placement scheme. The highest level constraint control is exemplified by simplicity. I first met Ken McIlvaine at the San Jose Convention Center soloing in a small booth with a brilliantly simple GUI. Enter the file name, target device, and target frequency, and press a big, huge Go button. That was it. Seductively simple and reasonably effective, but insufficient for today's bandwidth-driven applications. One vulnerability to such simplicity is the tendency to over-constrain the target frequency. For example, given a target frequency of 245.76 MHz, the standard FPGA route result has a net delay distribution curve. Some fast, some slow, most in between, but all hopefully under the prescribed 4.069 nanosecond max. Designers inclined to gain margin by cranking up the clock constraint to something like 300 MHz will find that while most nets might meet the new 3 1/3 nanosecond constraint, a few nets will fail the real 4.069 max requirement. The CXI ECA does not have a route delay distribution curve. Instead, the entire device has one rating, a unit delay, and all interconnections are guaranteed a priori to meet this device max. Another popular timing constraint method is to specify time domains and their relationships. For example, these 4 time groups spawn 12 constraint relationships. When Xilinx first introduced this constraint mechanism, synthesis tools auto-generated hundreds of groups with millions of constraints. Such over-constraint paralyzes timing-driven routers and post-compilation analysis tools. The CXI ECA has neither the need for nor the problem of specifying such time domain constraints. Altera's assignment editor provides a reasonable balance between overcomplexity and undersimplicity. For example, on this screen, device I/O standards may be easily constrained. This screen also makes it easy to edit individual I/O locations of any device pin. However, for the CXI ECA, it's unnecessary to place individual signals because the I/O are bus ports, not bit pins. Altera's pin planner allows placement of signal buses. Any bus in the netlist can be dragged and dropped to any I/O bank in the device. For example, here, the 3-bit MIMBA bus is dragged to and dropped on the upper left I/O bank. Altera's chip planner allows placement of logic. Consider this 71K logic module device. Assume you wanted to configure it with a design pipelined across the chip. You might expect the pipelines to end up equidistantly spaced if all are clocked at the same frequency. But let's also say the last 2 stages are running twice as fast as the rest. Then you'd want the latter 2 stages to closely relocate accordingly. Here's a snapshot of the unconstrained placement. Pretty good, but not quite what we'd expect. Adding general region constraints improves pipe placement, and tightening up the regions improves placement even more. Xilinx has a floor planner that allows drag and drop. From a hierarchy window, any design module can be selected and dropped anywhere into the FPGA array. This was exceedingly useful before FPGA arrays got so large. This concept is once again applicable to the coarser-grained CXI ECA. After constraints, the design is compiled, largely an automatic step. In prior art FPGAs, it consists of 4 phases: target, map, place, and route. Targeting is conversion of the behavioral netlist into device family-specific constructs. Mapping is aggregation of those constructs into device family-specific resources. Placing is correlation of those resources with device-specific locations, and routing is selection of specific interconnect segments between sources and their destinations. The final product is a device-specific physical netlist, not to be confused with a configuration file. Originally, this was a straight shot beginning to end, with min-cut mapping, simulated annealing placement, and shortest path routing iterations. Once a netlist was converted, the mapper was stuck with the operator conversions. Once a design was mapped, the placer was stuck with the mapping aggregations. And once the netlist was placed, the router was stuck with the component locations. Later tools added minor placement tweaks with rip-up and retry feedback between route and place, and some results could also be enhanced with rip-up mapping feedback between place and map. The first phase of compilation targets a specific device by converting behavioral operators into equivalent resources. If there are multiple implementation options, parameters like speed requirements drive the selection process. While automatic per-operator conversion is easy, automatic conversion of target-agnostic tasks and apps is not. The greatest algorithm conversion success derives from device-specific libraries. The more architecturally aware, the better. The second compilation phase is to map the netlist instances to target device resources. In this example, 2 flops are mapped to 2 FDs in the same configurable logic block, but not a specific CLB, and signals are assigned to the block ports. The third compilation phase is to place the mapped logic in the target device. In orthodox FPGA design flow, initial placement is traditionally done using the random seed shotgun technique. Placement is then agitated using Iron Age simulated annealing algorithms in which impurities are driven to the edges of the crystal lattice. At the end of the heating cycle, object attraction is calculated based on internal, I/O, and critical net weightings. And in the cooling cycle, the weighted bonds draw related components toward each other. But suppose you had an 8-bit register with one control line, each bit connected to an input pad, and another 8-bit register with one control line, each bit connected to the first register and to an output pad. You'd expect to get a placement something like this. The problem is, simulated annealing disadvantages structured objects, so auto-placement tools are more likely to give you something like this. Considering that for just this 12 by 12 exemplar, the incredible number of placement permutations, it's no wonder why the placement phase for FPGAs can take hours. The fourth and final phase of compilation is routing. Recall from the architecture presentation that in prior art FPGAs, every single node net has millions of connectivity options. And it just gets worse for multi-node nets. CXI ECA compilation is similar, but simpler. Targeting is conversion of the behavioral operators into element instruction contexts. Mapping is aggregation of those contexts into elements. Placing is correlation of elements within specific cluster zone locations. And binding is subscribing element input queue destinations to their element output queue sources. Targeting has already occurred when implementation is done using target-specific libraries. Because of the full interconnect architecture, no iterations are required for binding or placement, which means neither rip-up and retry placement nor context element remapping are needed. This greatly reduces compilation time from hours for FPGAs to seconds for an ECA. ECA targeting is done during implementation. That is, prepackaged function operators already target device elements. In a multi-context ECA, mapping gathers operators into element context sets. These context sets are placed within the array, and context binding assignments are made through additional queues if necessary. ECA mapping and placement are greatly simplified because every element in every zone has unit delay connectivity, so it doesn't matter where a context is placed. All connections being unit delay preserves performance, and this greatly simplifies simulation and timing analysis. The second simulation step is performed on the fully placed and interconnected design. In prior art, this is complicated by bit-granular route segment delays and gate-level logic optimizations, where the sheer volume of minutia obscures the goal, which is to confirm cycle-accurate functionality and validate overall performance. Such time-consuming gate-level SIMs are neither desirable nor necessary in CXI ECAs. Because the CXI ECA is an object-oriented, cycle-accurate architecture, cycle accuracy can be assured from simulating a behavioral model. This simplifies both simulation and analysis. After simulation, the next step is to analyze the design. Find out if it meets all user constraints. Analysis falls into two primary categories. Does it fit, and does it meet timing? Obviously, most fit analysis can and should be provided earlier. For example, final resource utilization is determinable after compilation. If the design is implemented with target-specific libraries, good resource estimates can be made during implementation. If it doesn't fit, common mitigations are to move to a larger part, refine or relax constraints, reduce or re-implement functionality, or repartition the design. By far, the worst problem in prior art FPGAs is performing and verifying timing analysis. The simplest failure class is route-related. Long paths and setup hold violations, most often caused by signal overloading, overly wide or deep combinatorial logic, and non-optimal placement. Prior art timing analysis tools are primarily focused on this problem class. Mitigations for this class include move to a faster part, more expensive and more power, choose a different part with more route resources, reroute with some new magic seed if you believe in magic, increase the clock frequency, not always an option and takes more power, change constraints, relax some, tighten some, relocate others, re-implement, use faster library components, adjust next state equations, move late signals forward, add pipes, and some software like DSP Builder does this, duplicate paths and functions, try to defeat the smart compilers that recognize and delete that redundancy, or decrease functionality, repartition the part. Tracking down bad paths requires a separate tool, the timing analyzer. This tool will generate dozens of reports. For example, the top failing paths. Here are the first 70 of 200 for this design. For each and every path, you can get additional information, including the path summary of node points, launch and latch clocks, data arrival versus required time, and slack violation, statistics listing timing relationships, skew, delays through the various physical entities, data path arrival delays and required path delays, a waveform showing launch clock edge, latch clock edge, when the data is required, and by how much it missed, here by 0.345 nanoseconds. And extra fitter information like what cell types are included in this path and where the path cells are located in the chip. With all this information, you can now track down this path in the chip. In Altera's chip planner, after setting appropriate layer settings, selecting an area, and enabling connections, a rat's nest is displayed. If you mouse over a wire, an additional box pops up with net source location, complete hierarchical net name, hold time, and setup time. Then you can inspect the source block. In this view, you can track through a signal's delay elements. In this example, maybe the path delay is exacerbated by non-optimal logic packing. The bad news is, in such prior art, you may have to do this analysis for each and every bit path violation after each and every route cycle. The good news is, in a CXI ECA, you don't have to. There are no long paths, setup or hold violations, overloaded signals, or overly wide, deep logic. The ECA, like an ASIC, has eliminated this simple but onerous class of timing error. Another timing failure class comprises design-related performance issues such as excessive latency, pipeline too deep, mismatched pipeline or slack, data streams misaligned, or inadequate bandwidth, insufficient computation in the allotted interval. Such issues might be introduced by pipeline insertion during compilation and necessitate a return to implementation. After all constraints are met, the design is ready for download onto a live board. Configuration is largely an automatic step, except for all the options. As this composite prior art download screen suggests, choices must be made for configuration modes, slave versus master, serial versus parallel, parallel bit width, and load source and device type. After generation of individual device configuration files, aggregate configuration files can also be created for multi-device chains. Now download is a simple button push, and wait for the green light. Optional readback is usually available to verify the download. By contrast, the CXI ECA has no mode, width, source, or device choices to make, since configuration is simply another message file transfer. And this is one reason why, unlike FPGAs, ECAs are actually in-field, dynamically, and partially reconfigurable. Analogously, microprocessor code must be compiled, downloaded, and optionally verified. After download, the design must be brought up, proven to work under real-world conditions. This step is critical for cases impractical to simulate or for detecting and resolving problems not exposed by analysis. The long list of problem cases falls into two general categories: physical and logical. While physical problems aren't design problems, they are obstacles to bring up. These include having a bad device, board, or test bench. The target device might have a die defect, or its I/O could be blown by mishandling, improper operator grounding. The device might succumb to infant mortality. It was good when installed, but dies after a few days or weeks of operation. A board might have some other part bad, or wrong, or missing. Traces might be shorted or open. Layout might introduce noise or crosstalk. Rework might be done incorrectly, or switch and jumper settings might be incorrect. Test bench cables might be shorted, open, improperly grounded. Connectors might have bent pins or floating grounds. Power supplies might be too high, too low, or unable to supply sufficient current. Or stimulus equipment might be improperly set up. In addition to bad data arising from physical problems, logical problems usually arise from misguided assumptions. Simple things like getting signal levels wrong, high instead of low, or missing a pull-up or a pull-down on a tri-state line. Unexpected initial conditions like reset states or register or memory contents. Errant accesses using the wrong storage address which work during simulation but not in situ. Resource sharing conflicts with misbehaving IP. Misinterpreted data characteristics, format, precision, boundaries. Unanticipated data stream behavior, packet size, count, intervals, jitter, and protocol violations like unsupported features, or worse, improper implementations. For example, with a hand-built embedded logic analyzer, I once uncovered a DMA scatter-gather problem in the Intel Neptune chipset. So, there are lots of reasons for lots of debug support for bring-up, because no designer is perfect. Recall NASA's $125 million Mars Climate Orbiter, which was lost because spacecraft engineers failed to convert from English to metric measurements. Minimally, bring-up tools need to upload static and quasi-static data such as configuration, state, register, and memory contents. Debug tools also need to embed analyzers with programmable triggers and capture transient data. Performance tools should be able to monitor, analyze, and report on data stream behavior and attributes. In the early FPGA days, we used to route single signals out of a device pin to a PCB test point, kind of like a hardware printf statement. The problem was, after loading the primary configuration, such test point routes get the last available interconnect resources, that is, the worst, often resulting in a problem called vaporization, where pulses on especially long traversals eventually fail to cross voltage thresholds and erroneously appear inactive on the output. This problem cannot occur in the CXI ECA. As if that wasn't bad enough, the FPGA problem gets worse for multiple signals, each of which has a different route delay, not indicative of their true alignment. Because the CXI architecture is all unit delay and ports are all bus granular, the ECA will not have this problem either. Nowadays, FPGAs overcome this problem by heavily pipelining signals from their point of capture to their point of deposit. Of course, to align the signals, the same number of pipes have to be added to each path, greatly increasing resource consumption and competition and compromising timing of the original application. Furthermore, the entire design, including pipelined capture logic, must be recompiled, replaced, and rerouted for each and every change. Such costly iterations are not required to bring up a CXI ECA. Here's a snapshot of Altera's Signal Tap Logic Analyzer, representative of the current state of the FPGA Logic Analyzer ART, a typical waveform view. Useful, but there are significant opportunities for enhancing this bring-up feedback experience. Finally, we arrive at the last step of the design process, archive. Notice this step is not labeled document, the stuff designers did when they thought they were done. That's old school, dead. The designer should be documenting the design all along, state diagrams, timing diagrams, tables, whatever. Old school archive collected and zipped relevant files manually. Today, this step is automated. The tools know, or should know, what's relevant, which is everything necessary and optionally helpful to successfully regenerate a project. A single button not only archives all files, but preserves appropriate hierarchy to successfully transport a project. This also implies a symmetric unarchive capability that reduplicates the appropriate hierarchy of the transported archive. The motives for proper archival should be obvious. Users need to upload problems to FAEs, who must be able to fully duplicate those problems, and FAEs need to download solutions to users, who must be able to fully replicate the solutions. Engineers need to hand off designs to other teams for test, validation, and verification, who in turn need to return it for fixes, upgrades, and modifications. But most commonly, archival is about maintaining sufficient incremental design control and information so the next designer will understand the design well enough to later be able to retraverse all the design steps. And 9 times out of 10, the next designer will be you. To summarize this comparison between FPGA prior art tool requirements and CXI ECA tool opportunities, both need to perform market research and product specification steps, and both would benefit from a multi-device partitioning tool, a complex undertaking for FPGAs, but simple for ECAs. Implementation tool granularity for FPGAs is down at the bit and gate level, but for the ECA is up at the bus and block level. Of the many implementation methods, text-based HDLs are most common for FPGAs, but not optimal for ECAs. Conversely, C derivatives have not been successful for gate and LUT-based FPGAs, but would be quite suitable for ECA executive layers. FPGA graphic implementation by schematic has largely been obsoleted by GUI-based wizards. For the highly structured ECA, block diagrams are still very suitable, especially as derived by macro generators. Functional simulation cycle accuracy can never be achieved for FPGAs prior to compilation because gate and route delays are unknown. But for the unit delay ECA architecture, early simulation can be cycle accurate because all delays are guaranteed a priori. For similar reasons, gate and LUT simulation time for FPGAs can run for hours, but for ECAs is mere minutes. Constraint types for FPGAs primarily control partitioning, placement, and timing, the latter meaning individual net timing. For the ECA, partitioning and placement constraints are very applicable, but net timing constraints are entirely unnecessary. FPGA tools don't even have the bandwidth to innovate the class of performance constraints, samples per second for example. CXI tools do, precisely because they aren't burdened with all the individual net timing. Constraint entry methods include text, schematic, and block diagrams, HDL params, and IDE utilities, all applicable to FPGAs. For ECAs, constraint application via text and block diagram is useful, but it's more convenient from a GUI utility. Specialty tools for constraint application include pin and I/O bank planners, and chip and floor planners, all employed by current FPGA tools. Pin planning isn't applicable for the bus granular ECA, but I/O bank planning is, as is floor planning, but at a higher operator and region level. Presently, FPGA tools are too overwhelmed with bit-level minutiae to implement a bandwidth manager, a tool to constrain implementation by high-level parameters such as samples per second. However, the ECA is perfectly architected to take advantage of such a next-generation tool, because ECA granularity is up at the word operator bus level, whereas FPGAs and their tools are down at the lowest bit gate signal level. This means constraint complexity for FPGAs is very high, but relatively low for the CXI ECA. Prior art FPGAs in the CXI ECA have in common compilation phases target, map, and place, but the FPGA's costly route phase has been superseded by the much more efficient ECA binding phase. Because the FPGA phases are all bit-based, the number of permutations is in the billions and takes hours to consider, whereas the ECA phases are all operator and bus-based, and permutations far fewer, take only seconds to consider. Post-compilation simulation for FPGAs means considering physical attributes of route delays, net loading, and driver strength. Because ECA timing is all known a priori, like a microprocessor, its post-compilation simulation can still be performed with a behavioral model. Again, this costs FPGAs hours for simulation, but seconds for ECAs. And when you're done, the FPGA sim may be cycle accurate, but you don't know how long a cycle is until timing analysis is done, whereas post-compilation ECA sims are always cycle accurate, because, like a microprocessor, cycle time is known a priori. Post-compilation timing analysis is fraught with problems, like analyzing long paths, setup and hold violations, signal loading, and equation depths and widths, all of which must be analyzed in FPGAs, but none of which are applicable to ECAs. More abstract problems like excessive latency, mismatched pipeline slack, and insufficient bandwidth must be analyzed by both. The primary method for FPGA analysis is the timing analyzer, a tool that's focus is necessarily bit and net-based, requiring a total effort in excess of weeks, whereas the ECA raises the analysis focus to data stream bandwidth, an effort measured in less than days. Obviously, the ability to download and initially configure devices is required by both FPGAs and ECAs, but neither dynamic nor partial reconfiguration is feasibly supportable for FPGAs. However, it is for ECAs. Bring-up tools are primarily confined to in-circuit logic analyzers, bit level for FPGAs, transaction level for ECAs. Higher level embedded performance monitors must be user designed for FPGAs, but should be a part of the ECA Bring Up toolkit. And lastly, archival is universally applicable. So, what do we conclude from all this? First, that tool form follows device architecture. In particular, that device granularity determines tool abstraction level. For fine-grained FPGAs, their tools require many fine-grained decisions and manipulations at the lowest level. But medium-grained ECAs, accordingly, have simpler tools requiring far fewer manipulations, allowing for a higher-level programming model. Second, FPGA architectures and tools are buried in flexibility, and ECAs needing less are less demanding of their tools and users. And third, it should be obvious that ECA tools have raised the bar on all the most onerous design tasks: constraint, simulation, and analysis. In fact, the CXI ECA is in the sweet spot between FPGAs and DSPs and microPs, retaining the data flow acceleration advantage of FPGAs and the higher level programming bring up and debug model of the microPs, while avoiding the disadvantages of burdensome FPGA minutiae and avoiding the memory access bottleneck of von Neumann architectures. And the CXI ECA advantage is even more apparent with new features that have no comparable basis in prior art, the subject of the next presentation.